So thanks to the organizers for inviting me to this conference and giving me a chance to visit what is also my home institution. So it's a bit funny. But anyway, okay. So I'm going to talk about cohomological representations of real reductive groups, and this is based on joint work with Dipendra Prasad. Okay, so let me start. Okay, so G will always be a connected reductive group over the reals for me. G will stand for the Lie algebra of the real Lie group, and K inside GR is a maximal compact subgroup. Okay, so one can keep in mind examples like GLNR, and then the maximal compact is ON, or symplectic groups, okay, and various classical families. So there is a notion that I want to just say, recall, which is of an admissible GK module. Okay, so that means one basically looks at a vector space, typically infinite dimensional, with compatible actions of G and K. G is the Lie algebra, and K, and there's the obvious condition that the differential of the K action is the same as the action that you get if you consider K inside G. And there's a certain, so I don't want to go into all that, it is anyway well known, these things, and admissibility is the condition that every vector is contained in a finite dimensional K stable subspace, okay? So the point of this is that, work of Harishchandra in the 50s and 50s, I guess, showed that there is the obvious functor from any category of reasonable representations of GR. So I'm not going to define reasonable, but obviously one has to define it. Two admissible GK modules provides sort of, this functor is reasonably nice, and it reflects the, for example, irreducibles go to irreducibles, and exactness and all that kind of thing. I haven't, of course, defined reasonable and this functor, but the point is this achieves some sort of algebraization of the representation theory of a real reductive group. And depending on your choice of the meaning of reasonable, there are different reasonable choices for reasonable. You can have different adjoint functors going the other way. Okay? But the important point is that among these are unitary representations of which there's no sort of ambiguity possible. Namely, you just have a representation on a Hilbert space and it's continuous, etc. And when you restrict it to that, you get what are called unitarizable admissible GK modules. And here this is sort of really even better. Sort of there's a canonical adjoint functor, and these are very close to being an equivalence. So in particular, okay, so I should, of course, this is slightly wrong, I have to put an admissibility condition here to get the same thing, but it doesn't matter. And these functors, you can put the word irreducible everywhere. So on this side, of course, irreducible refers to closed subspaces. On this side, it's just subspaces stable under G, and everything works nicely. This is all in the work of Harishchandra. Okay, so this is all due to Harishchandra. So this basically achieves an algebraization of the theory, substantially, of what we want to look at. Okay, so then we can ignore the general thing. So henceforth, I'll just use the word irreducible unitary representation, etc., to mean irreducible unitarizable GK module. Then, okay. So there's one more point that we need to say, that the center of G, so this is the center of the universal enveloping algebra. And this is known to be isomorphic to the symmetric algebra on H where H inside G is a maximal, is a Cartan subalgebra. So that's a maximal, yeah, G is reductive, so maximal abelian subalgebra. Well, okay, the Cartan subalgebra. And the Weil group is the, W is the Weil group of G and H. So the point is that characters of the universal enveloping algebra are exactly in bijection with the dual of the Cartan modulo the action of W. Okay, so that's the spec of this ring. And it's an old theorem of Harishchandra that, I mean, everything I've said so far is due to Harishchandra, of course. It's an old theorem of Harishchandra that this, there exists only finitely many V inside GK modules, admissible, etc., irreducible, admissible, with given infinitesimal character. Okay. So cutting down things by the infinitesimal character already reduces the classification problem for irreducibles to a finite list. Okay, this is all probably in the early 50s. Okay, so I want to make one definition now. Okay, so maybe just a remark for later use. If E is a finite dimensional representation of GC, okay, so the complex points of G, so then this is given by a highest weight theory. So this has a highest weight, say lambda, then the infinitesimal character of E, okay, is given by the orbit of lambda plus rho. So rho is the half sum of a system of positive roots. Okay, it doesn't matter. I'll need this rho, this business later, but I'll just remark on it here. Okay, so as I said, this is already reducing. If you fix your infinitesimal character, there are only finitely many. And among these, somehow, there are the nicest representations of real groups are the cohomological ones. So let me make the definition. A cohomological representation for G R is an, of course, I'm going to say irreducible, admissible GK module, but I don't want to say all that, such that is a V such that the following group is non-zero, so I'll explain this in a moment. Okay, so is non-zero for some finite dimensional GC module representation E. Okay, so this is our definition of cohomological representation. So let me say what this means. So here I'm taking an X in the category of GK modules. You can put an admissibility condition, let's put one. So that's an abelian category. E check is the dual representation of E, and V is our given module. And this is the X. For those who are familiar, this is the definition of GK cohomology, which is usually written this way. These two things are the same. If you're familiar with this definition in terms of an explicit complex, just take that. Just to note that here this becomes V tensor E, here you get X between E dual and V. Okay? So this is a condition on a representation. So a remark is that, okay, so I haven't put a unitary condition, but essentially I'm really only interested in unitary ones. So let's implicitly, I'll be assuming if I forget to say it, everything will be unitary from now on, right? Of course, the definition makes sense in general and one can ask about them, but somehow for the purposes of automorphic forms, unitary ones, at least at the beginning, are really the most important ones. And you don't need to really worry too much about the others. Okay, so the first remark is that, so we need to have some non-trivial representation. So the trivial representation is always cohomological. So let's just write this as 1 is cohomological for the coefficient system E being the trivial representation. Okay? So this is a non-empty set. The second statement is, okay, sorry. So I'm sorry, I'm going to change my definition, okay? So I'm going to change that in a second because it's important. So it's a well-known fact about real Lie groups that the component groups of K and G are the same. Namely, K meets every component of G. So we can also take a slightly weaker definition that you only require cohomology with respect to G, K naught. So I'll give an example of why this is relevant and we'll see why it's relevant. Okay? So this is slightly weaker than the notion. So the usual notion uses GK instead of GK. But this is a very small difference, but it's important for the formulation of some of our results. So this statement is true even with GK. So for example, sorry, K upper naught, yeah. K naught is the connected component of identity. Yeah, sorry. So the group G, no, it's a connected reductive group over R, so its real points may not be connected. Okay, so GL and R. Okay, okay, so in this case, so for example, the sign representation. Okay, so the representation sign of determinant. So I'll give it a name, epsilon of GL and R is GK not cohomological, sorry, I might by mistake put the thing, but not GK cohomological. So we're slightly increasing what is traditionally called cohomological. It's a very minor difference, but it plays a role for us. Okay, so far we have only a trivial example and a slightly non-trivial example, but then the important example is that if G has discrete series, or rather GR has discrete series, okay, so by of course Harishchandra, this is if and only if the rank of G mod center is equal to the rank of the maximal compact, okay, then they are cohomological. So the discrete series were parameterized by Harishchandra by certain, well, the discrete series L packets were parameterized by certain dominant weights, and that gives you, if you have an L packet, that dominant weight tells you what E check, or the infinitesimal character tells you what E check you need to put here. So the important remark is 4, is that if V, if this is non-zero, it doesn't matter if I do this thing, then the infinitesimal character of V is the same as the infinitesimal character of E check. This is hardly surprising because the center, this is an X between two things. It's roughly like X over a ring. The center of the ring has to act by the same scalar on both sides. Okay? So this is called Wigners' lemma. Okay? But you see that once you fix the infinitesimal character, then we're talking about, because of this finiteness theorem, we're talking about finitely many representations. Okay, and this is another remark, and another remark which I'll just make is that thanks to Matsushima's formula, if you have an arithmetic subgroup of G, I won't say exactly what that means, then the representation, the cohomology is given by some multiplicities which depend on gamma times these spaces. Okay, so these representations are really, that's why they're interesting from the point of view of automorphic forms. So this is a, whatever condition is, I'm assuming this is compact. Okay, but in the non-compact case also there's something. Yeah. Oh, sorry, so I'll put K here, okay? Yeah, it works either way. Okay. Okay, so this is what we have, and then the last remark is that actually, so, I'm talking about these things, but these were already classified a long time ago, classified by work of, okay, so there are several names, but the final paper in the subject is written by Vogel and Zuckerman in 1984. So maybe the beginning of the classification was work of Parsarthi, and then Kumareshan, and then Zuckerman and Spee, and then Vogel and Zuckerman proved the general thing. And they're classified by them in terms of a procedure called cohomological induction. Okay, so I hopefully will say a little bit about this at the end, but it's a process which is very much analogous to, for those who are not familiar with real groups but familiar with finite groups, it's very much analogous to Deligne-Lustig theory. You sort of induce characters from certain non-real parabolics. Yeah? Okay. But this was classified, right, okay. Okay, so that's what I wanted to say about cohomological representation. So this is the sense in which they're important because they give us at least a beginning of a whole modulo, the much deeper question of multiplicity on the cohomology of objects which are locally symmetric spaces or Shimura varieties in some setting. Okay? Okay, so now we want to talk about parameters and packets. Okay. So this already has occurred in previous talks. So remember that the local Langlands conjecture, okay, so this is actually not a conjecture. Local Langlands over R gives a mapping of irreducible, admissible GK modules modulo isomorphism, and it's a finite to one map to L parameters. So what are L parameters? They've appeared in other talks. So, but I'll define the real way group in a moment since it hasn't appeared before. L parameter. So that's a continuous homomorphism. So continuous. I'll remark on what the way group is in a moment, yeah, for those who are understanding, and all for the L group. Such that with some conditions, yeah. So basically, it commutes with the projection. I'll say more about this. And 2, phi consists of semi-simple elements. And maybe there's another condition about admissibility, which I'll ignore now. Okay, so what is this? So this was, of course, proved by Langlands in using the work of Harishchandra in the early 70s, right? So here, WR is the real way group. The p-adic way group has already appeared in several talks, but this is actually much simpler. So it's just, one can think of it as 2 copies of C star. One is indexed by this extra element J. J has the property that J squared is -1. And J inverse is Z bar. So basically this is the group. Okay? So it's a very simple sort of group. And it contains this C star, which is the way group of the complex numbers, as this copy. Okay, so yeah, and then now LG is the semi-direct product as usual of the, okay, so what is this? G hat is the Langlands dual group, which appeared in Anne-Marie's lecture and in Binshu's group lecture. So of G, one takes G over the complex numbers and then takes a dual group, which is, so recall that the duality exchanges SLN and PGLN, and it preserves GLN, it exchanges symplectic and orthogonal groups. There's a duality. And using the fact that G is defined over R, you can produce an action of the way group using the complex conjugation action over here, and then you take that semi-direct product. Okay, so this has appeared in some other instances. So the local Langlands conjecture says that there is a finite to one map, and the fiber of this, fibers are called L packets. Okay, so this is where the perhaps first L packets arose. The thing to remark is that for GLN, this is actually a bijection. this is a bijection. So what that means practically is that, oh sorry, I should have taken modulo conjugacy. Okay, so modulo G hat conjugacy. So the parameters go into this group, and then one considers them mod the conjugacy on by G hat. Okay. So for GLNR, this is a bijection, so it actually provides a complete list. It tells you what the irreducibles of this in this thing are. So we'll use this because one of our applications will be to do things in terms of classical groups in GLN. Okay, and there's one more definition. Okay, this is standard, so phi is tempered. Okay, so let's look at, let me give a name to this set. Let's call this set phi of G, and if I have phi of G, an element phi is tempered, it's called a tempered L parameter if phi of C star is bounded, or the whole group is bounded in the complex group G hat. So these are tempered parameters. Okay, so yeah, I didn't do a great job of this, but let's just, I wanted to be able to, so I'll just mention that there's irreducible admissible. This is got this map to phi of G. That's what I've just defined. Inside that are the unitaries, isomorphism classes, and inside that are the tempered representations. And this is not well, over here you have the bounded ones, and they correspond to tempered representations. Okay? So the bounded parameters give tempered L packets. There's no hope of describing unitarity in terms of parameters. Okay. So now, given this setup, there is an obvious notion, where namely, given GH and G, two real reductive, connected reductive groups with a homomorphism of their L groups. Okay? So that means a homomorphism, it just has to commute with the projection to R. Everything has to commute with the projection to R. Okay? So this is assumed, so this is called an L homomorphism. We can transfer L packets of representations from H G. Okay, so we've defined this category of, this class of cohomological representations, and so the obvious question is, can you tell from the parameter which representations are cohomological? And then the second obvious question is the property of being cohomological preserved by Langland's functoriality? Okay, so that's the questions that I'm going to address. So the first question, so cohomological representations are not going to be preserved by functoriality. I mean, you don't expect this in general. Okay, so why is this? This is elementary because you see a cohomological representation has to have the same, somewhere here, this one, it has to have the same infinitesimal character as a finite dimensional representation. And that property is not preserved in general. So for the easiest example of that is that if you take GLN cross GLM and you take GLN plus M, the dual groups are, so this is H and this is G. So here you just take the obvious inclusion of dual groups. And if you look at this, call this, say, I, or iota. Iota of the trivial representation does not have the infinitesimal character of a finite dimensional representation. This is an easy exercise because I said that the infinitesimal characters of finite dimensional representations have a very special form, right? These are non-singular, as they're called. So this is not true, yeah? So this is certainly not going to be true in general, and this is the simplest example. So you see, certainly, if you think about it, you certainly need to, okay, let's say certainly should restrict to L homomorphisms, I hope it was H to G, which take the trivial representation to the trivial representation. Should meaning that may not be the only way to do it, but that might be a start. So I'll explain a little more why this is true. Okay, so I'll come back to this remark and come back to the question of functoriality. The other point is that the question is somehow more natural to consider on the level of A packets. Okay, so I'll explain why. And anyway, the nicest results come out for A packets, so that's why that's correct. Okay? Okay. So, at this point, okay, I'm roughly on track. I wanted to say one thing, which actually was already in Anne-Marie's talk yesterday, is that, let me put this over here. Parameters live inside a certain Galois cohomology group, right? Because you just take the second coordinate of the parameter, so to speak, in these terms, right? And here you can obviously twist by the cocycles of WR inside the center of the dual group, just by multiplying cocycles, and this preserves phi of G. Okay, so this is twisting action. And if you look at an example, for example, GLN, the H1 of the center is basically, it comes out to be squares, things which, square roots of unity. And so in this case, so example GLN, this is Z mod 2. Oh, it's plus minus 1, let's call it. So you can always twist parameters by things like this, and this Z mod, this twisting is exactly what we will have done by going to K naught instead of K. Okay? Okay, I'll come back to this thing. So morally, the reason I changed the definition from K to K naught is basically so that the set of parameters I'll get will be stable under that twisting by the cocycles of the center. Okay, this is not terribly relevant, but this thing. Okay. Okay, so coming back to what I was saying here, so I'll discuss GLN again later in more details. Yeah, I'll discuss GLN later. So we want to look at a condition which will take the trivial representation of the trivial representation, because that's our primary example of cohomological representation. And then there's of course sign and stuff like that. Already the discrete series, it becomes slightly non-obvious what you expect for the transfer of discrete series. Okay, so here's a condition. So let me just define, I don't know if a regular unipotent element in a complex group G hat, say, is a regular element which is unipotent. So that means that the regular means that the centralizer, say call it U, the centralizer is of minimal dimension. And this is actually the rank of G hat, and which is unipotent. Okay, so they exist always and are all conjugate. These are all very classical things of Steinberg or somebody like that. And the second definition I'll need is that a principal SL2 in a complex group G hat is a homomorphism, say call it phi from SL2C to G hat, such that it takes the standard unipotent is a regular unipotent. So these are also all conjugate. Okay? And it's a fact that if something centralizes a principal SL2, then it has to sort of centralize both the regular unipotent, which comes from this one, and then the opposite guy, and it's forced to be actually in the center. So remark, if G inside G hat centralizes a principal SL2, then G is inside the center. This is the point. So the principal SL2 is a big group. Example, yeah. In GLN, you can always take a matrix with a single Jordan block, a unipotent matrix with a single Jordan block. In general, the sim n inside GL, whatever it is principal. Okay. Okay, so let me state the first theorem we have. Let G, say I'll call them G1, G2 be connected reductive, and rho from LG1 to LG2, such which takes a regular unipotent in G1 check hat to a regular unipotent in G2 check. Okay? So I've restricted to L homomorphisms which have a good property with respect to regular unipotents. Then two things happen. Sorry, I realized that I have to make a definition, so I'll come back to this here. Sorry. Okay, so I was spaced out a bit, right? Okay, so as I said at the beginning of that board, back there, the correct way to consider the question is on A packets. So I have to tell you what A packets I'm talking about here. Of course, this was already, A packets were introduced yesterday, but let me just say, so author parameters, I'll come back to this statement of this theorem, don't worry. Are there any questions? Okay. So author parameters are an enhancement of Langland's parameters in the sense that they, so yesterday we saw them in Bin-Shu's talk, except that here the real way group is very simple, so there's only one SL2. So it's a homomorphism from WR into SL2 such that psi restricted to WR is a tempered Langland's parameter. And yeah, that's essentially it for me. Okay? So basically you have to take a tempered Langland's parameter and find a commuting SL2 inside the group. Okay. So there is a mapping from this into phi of G where psi gets mapped to a particular Langland's parameter which is not this restriction, but it's given by psi of W and okay, so this norm in the way group, I'm not going to say anything about it. Okay, so but just remark that there is a thing, there is a mapping like this, and if I look modulo conjugacy, it becomes a isomorphism in injection. Okay, so other parameters are somehow an enhancement of Langland's parameters. Not all Langland's parameters can be enhanced this way, and the general theory is that there are packets of representations, unitary representations And at the Archimedean place, these have been defined. So this is called an Arthur packet. At the Archimedean place, they were defined by Adams, Barbash, Vaughan. Okay, I'm just going to abbreviate the names. ABV a long time ago. The packets for cohomological representation. So cohomological unitary representations, as I said, they were classified by Vaughan and Zuckerman, and then soon after, Adams and Johnson did the same for, soon after that, for cohomological representations. And then, because of the work of Arthur, these have been defined again for classical groups. Okay, so these are certain different packets consisting of unitary representations. They are more subtle, they overlap, that's the big point. Okay, so I'll say that these packets have been defined, but we don't really care too much about that. And there is work of many people saying that comparing these various definitions, and most notably Arancibia, Mogla, and Renard within the last few years. And it looks like you have to have an A in your collaboration to work with the subject. Anyway, so, we should find somebody. Anyway, so comparing these definitions. So the upshot of this, a lot of this work, well, for us, I mean, not in general, is that the following implication is that there is a good notion of cohomological A packet. I'll say and cohomological A parameter, but I'll say a little more about that later. So what do I mean by that? What I mean is that the A packets defined by all these people coincide for cohomological representations. That's probably implicit here. Whenever they can coincide, they do coincide. Otherwise, one just uses the Adams-Johnson packets. And the fact is that a representation is, if one representation is cohomological in the packet, then everything in the packet is cohomological. So that's why the notion of cohomological A packet is well defined. Okay? So I'll just take this for the moment as a black box. If you're familiar with, cohomological induction and Adams-Johnson work basically imply this. But then you have to worry that you're talking about actual A packets, but you're talking about A packets. Okay. So now I can state the theorem. So the theorem is so I'll state the theorem in terms of parameters. So I've said that the notion of A packet makes sense. So let's pretend like the notion of A parameter makes sense. In fact, there is some clarification to be done. These works are not completely certain about the parameter, and that's basically one of the things we do. But let's say this. So then first, a cohomological A packet of representations transfers to a cohomological A packet on G2 of G1. Okay, so the forward transfer is good for cohomological A packets. And second thing, which is somewhat more striking, is that if an A packet, okay, so this will be slightly ambiguous, but I'll say that. If an A packet transfers to a cohomological packet on G2, then it is cohomological. On G1 to begin with. Okay? So the theorem is saying that basically under this condition on regular unipotence, A packets transfer well and it's exact. So something becomes cohomological if and only if it was cohomological to start with. So this is, okay, so I'm way behind. So let me just state this is theorem 1. To state theorem 2, I have to make a definition. A parabolic, and this is okay, I think I should have come up to this earlier because people might be tired, but this is a key definition this is maybe a key one contribution in this paper. A parabolic in G hat. Yeah. Well, there's a table exercise in Bourbaki which lists all the settings which happens where one of these is simple. Yeah. And it includes essentially all classical cases except SO odd. SO even, but SO even can be reduced to SO odd there's a trick in. Yeah, okay, so I didn't have time to write this down, but I'll just state the theorems. Yeah. So this is, I think, the key definition. A parabolic is called self-associate if it is conjugate to its opposite. Okay, so I mean, I'm saying its opposite, but there's not a unique opposite, but any opposite under the J part of under the other component of the L group. Okay? So then theorem 2, which is sort of proved at the same time as theorem 1, I mean, it kind of. Oh, okay, so let me say what this condition is. Okay? So, for example, if G is an inner form of a split group, then this is just the condition, the usual condition of being self-associate. Namely that the group is inside the group is just conjugate its opposite. So for example, in GLN, this means that it's a partition, a parabolic is a partition, and the partition should be palindromic in the sense that it should be like 1, 2, 1. This is allowed for 4, and this is not allowed. Okay, so it's just a parabolic which has an involution sort of thing. So that's in the split case. In general, if you have a complex group and you work out what this means, it means that the parabolic essentially comes from a parabolic defined over R. Yeah, and that's also a convenient thing. Okay, so let me state the second theorem. There is a map from cohomological A parameters, A packets or parameters, to self-associate parabolics in the dual group, which is a bijection if G is simply connected and the restricted to packets with trivial infinitesimal character of the trivial representation. Okay? So what I'm saying is that given any cohomological A packet, it essentially, if G is simply connected, it comes from a self-associate parabolic. So you see that cohomological A packets are really simple. They're just combinatorial objects. They are parabolics in the dual group with a certain self-association condition. And once you arrive at that, it's not terribly surprising that you can move them back and forth under a reasonable hypothesis on the L group. Okay? But there are a couple of tricky points involved. Okay, I should make another example here. So if you take sp2g, then any parabolic of the dual group, which is SO2g plus 1, is self-associate. Okay, so there's no condition. And this is always the case when the group has discrete series. When the group doesn't have a discrete series, typically it is a condition, but it's an explicit condition. It can be checked. Okay, so a corollary of theorem 1, which rather surprisingly was not, we couldn't find it in the literature, is that there exists a unique tempered cohomological A parameter. Always. Okay? With fixed infinitesimal character. Okay, let me just say it with infinitesimal character of the trivial representation. And it is easily described. It is given by, so tempered parameters are already A parameters. Remember, A parameters are parameters which have an SL2C factor, and tempered basically are trivial on this factor. So basically it's already a, and I can this parameter can be described very explicitly as follows. You take the following parameter. Okay, so I'll describe what this is. This is a parameter for SL2, yeah, SL2R, or sorry, PGL2R. And what parameter do you take here? You parameter of the lowest discrete series. And here you take a regular unipotent embedding. Okay, so we have an explicit description of the tempered parameter, and this description implies practically all previously known results on the question on functoriality. Okay, so I'll just mention because I'm actually a little ignorant of what's known, but this has been discussed in papers of Raghuram and Shahidi and Raghuram and Sarnobat, and essentially all those results are mostly they follow by explicit computation with discrete series parameters, but this explains why they're true, so to speak. Okay, so at this stage I can either, okay, well I have to do what I have to do, so let's see. So Ameya asked about this condition, right? So let me remark that we have a complete list of this holds in the following cases. Okay, so one is sp2g, so this is the dual group inclusion. SO odd inside GL the same. SO even, SO odd inside the, I mean SO even containing the previous SO odd. Okay. Yeah, then everybody's favorite exceptional groups, F4 in E6, 5 G2 in spin 7. Okay, so I'll just in SO8 and G2 inside SO7 inside SL7. Okay. And there are examples involving like the principal SL2, just SL2 sim n powers. The remaining examples are like this. Okay, so this is all the conditions that you get. But you see, this immediately describes the cohomological parameters for an odd orthogonal group in terms of cohomological parameters for GLN, for a symplectic group in terms of GLN, and for an even orthogonal group, you have to do some trickery involving that. But again, you get a complete description of cohomological parameters. So maybe I should mention that as like a corollary just to state. So I'll state it in. Because we have a complete description of cohomological parameters for GLN. Okay, so I'll mention if there's time. This is due to Spee. A long time ago, we get that a cohomological parameter for a classical group. Okay, so there'll be a caveat here, is simply a cohomological parameter for GLN, which is a parameter for the classical group. Okay, so this I haven't said this correctly. This is true anyway because of that table. And because of this, we get explicit descriptions. Okay, so the star is that something has to be done for odd, something extra for even orthogonal groups. That's this caveat here. Okay, so maybe I should give you the statement of space theorem and then that will become clear. The other thing I could do is explain how the regular unipotent condition comes about. Okay, so let me just actually explain what the condition relevance of regular unipotence is. Okay, so these two theorems basically follow from one observation or one theorem, which is the following that notion. So let me make a definition and then I'll stop. A cohomological A parameter. So you notice that I've been talking about cohomological A parameters just on the strength of the notion existing, but we can actually, I'll give you a definition now, and part of our work is really to clarify what the cohomological A parameters are, and that has some other applications which we'll look at. A cohomological A parameter of, so first I'll look over the complexes. Is, so I'm assuming that it's bounded on the, it's bounded on C star. That's the unitary condition. The temperedness condition is a homomorphism such that one, the infinitesimal character is that of a finite dimensional representation. Two is that the centralizer of the image of the parameter on the C star. Okay, so the parameter is going into LG. The centralizer in G hat of the image of the C star is a self-associate parabolic. In G hat. That's the definition that I made over there. And three is that when you restrict your, let's call this phi, when you restrict it to the SL2C is a principal SL2. Is a principal SL2 in G hat. Okay? So what I'm saying is that this is the characterization of cohomological parameters. Namely, if you restrict them to this is the Weil group of C cross SL2C, then they should satisfy these two conditions. It should have right infinitesimal character. The centralizer of this C star should be a self-associate parabolic, and then this guy is going into a principal SL2 in that parabolic. So that's how they commute. Okay, and the technical theorem which implies all the others is that such a parameter has an extension. So how is this? This is short of a author parameter over R because you have to just extend it to WR. So all you really need to do is prescribe the image of J in my notation, phi of J. And the point is it can always be done. Such a parameter has an extension to a parameter of a genuine author parameter, and the extension is unique if G is simply connected. Okay, so this is the technical, this is the theorem which implies the other result. Okay, that didn't go off, so okay, but I think I'm done my time, so I was waiting for that. But okay, so let me just make a remark about how, just in the 38 seconds I have left, how this implies. The point is that this condition on regular unipotence, where was it, is exactly the condition that allows you to move parabolics back and forth from G1 and G2. And self-associate parabolics move back and forth to self-associate parabolics. So once you know that your parameter is determined by what it looks like on the complex wave group, then you forget, so that once you have this theorem, you forget about all this thing and you're just dealing with combinatorial objects, namely self-associate parabolics. And that's exactly the condition you need to move them back and forth in a way which is really good in the sense that, what is the statement? The statement that, is that my 55 minutes or my full time? Oh, okay. Okay, so then I'm confused. Okay. So it's exactly the way in which there is, for any parabolic in the bigger group, there is a parabolic in the smaller group, such that when, well, you can just extend, okay, since I have 5 minutes, I'll do it here. Given any P inside, so I have G1 hat sitting inside G2 hat. Okay, so I'm pretending as if it's an inclusion, so I should have been a little there. In the theorem, you don't need, I may have made one, no, it's correct as stated, yeah. So let's assume that they are in G hat, G hat, G hat, G hat. So given a P inside G hat, I can always intersect it, P2, I can always intersect it with G hat, G1 hat, right? And conversely, given any parabolic here, you can always extend it to a parabolic here, extend it in this sense, yeah? But the point is that there are several ways to do that. And this condition on regular unipotence really allows you to distinguish a good way of doing that, right? And the good way is really good in the sense that the levy in the smaller group will be the levy, so let's call it L1 will be L2 intersected G1 hat. And the unipotent radicals work well. Moreover, regular unipotent in this levy will be a regular unipotent in this levy. And a unipotent in this levy cannot be regular unless it was already regular, okay? So this condition basically pins that down really nicely. And yeah, so that given theorem 3, I think then it's clear how everything goes. So I didn't get to state Spe's theorem, but it's very nice. Spe basically says what the cohomological parameters for GLN are in terms of just completely explicitly, right? So maybe I can just tell you what the parameters are. So basically, a parameter for, so a parameter of WR inside LG, which in now we're talking about GLNC, is a sum of, these are the irreducible two-dimensional representations of the wave group, and then I have to take some symmetric power, and then there are some one-dimensional factors, okay? And Spe tells you that such a sum plus one-dimensional factors, such a thing is cohomological exactly when it is of this form. Namely, a bunch of these are the discrete series on SL2, the two-dimensional representations of the wave group, okay, which is the same as discrete series. And this, and then that, subject to a certain condition, so a condition can be written down very explicitly. It's basically that the infinitesimal character should match. So I don't think I can fit it in here, in that little box, but then I'll be done once I do that. So let me erase another theorem somewhere. Okay, I'll erase these people. Okay, so what I'm saying is that a parameter like this is a cohomological parameter if and only if, this is Spe's theorem, this formal sum. So in this you can just consider nu to be a formal variable. So you take nu to the k plus 2 plus nu to the k minus 2, you multiply it out by this sum, so it jumps by 2 every time, the mk minus 2, etc., etc. Plus the same kind of thing for a, okay, must be equal to this formal sum, where now lambda is the coefficient system of the highest weight representation. If you want to take trivial coefficients, you can just drop this. So you see, this is just a formal identity, and you can check this. Yeah, and this is just the condition that the infinitesimal character of this packet looks like that of a finite dimensional representation. No different. The extra factor, so this Spe's original statement of the theorem doesn't allow epsilon here, but that's related to the compact group business. So the point is now that given this theorem and these embeddings, you immediately can just say that the cohomological parameters are those for which this is an orthogonal parameter. Okay, so that's a certain condition on the k's and mk's appearing. That's all. Okay, I think I'll stop there because, yeah. Okay.
So thank you very much for your interesting talk. Are there questions, remarks, or comments?